Sound is a pretty astonishing phenomenon. The ability to hear is one of the most important sensory modalities that enables us to process and respond to our environments. Sound is the transfer of energy as caused by a disturbance between an object and its surrounding matter that produces sound waves. In order for sound to be propagated, there must be a medium in which it travels through. When a disturbance is provoked, a sound wave will cause the molecules that surround it to bump into one another, causing rapid variations in air pressure. The matter compresses and rarefies as the waveform moves through it. Sound can move through many mediums. Gases, liquids, even solids can transmit sound. Each medium affects the speed or rate of the sound differently, depending on its individual properties. For example, the molecules in water are packed much tighter together than in air, and therefore sound waves move much faster and further when underwater. This is why sound is such an important source of communication for marine mammals such as whales. Their vocal expressions can travel immense distances across the vast oceans in which they roam. I'm sure you might remember the old-fashioned string telephone. Well, it works the same way. When you speak into the cup, your voice causes the cup to vibrate. These vibrations move in waves across the string pulled taut between you and the other caller. When they reach the cup on the other end, the vibration is transferred, and the sound is successfully transmitted from one end to another. The string telephone allows us to converse with one another from far distances, as the soft connective material of the cotton string, which has a higher density than that of air, allows the sound to travel much further. Since the particles in air are so spread out, the vocal vibrations will dissipate before they have a chance to travel very far. A telephone works in a similar fashion, except its mechanism is electric instead of acoustic. It contains a microphone, which uses a diaphragm to convert sound waves into electric currents that are then transported through wires, ultimately to be converted back into sound waves by the earphone on the other end. Let's consider the old thought experiment, which poses the question, if a tree falls in the forest with no one there to hear it, would it make a sound? Well, it might depend on how you define the essence of sound. If sound is just a mental representation constructed by the brain upon reception of molecular vibrations, the answer would be no. But although the sound may never be perceived or heard, a vibration is most undeniably created. A rather large one, I would say, resulting in some pretty serious sound waves. If a tree were to fall in a vacuum, however, the answer would be no in every sense. While there's still a release of energy, there would be no matter for the sound wave to be propagated through. That's why there is no sound to be perceived in outer space. There must be a medium, and in the emptiness of deep interstellar space, there is no matter in which the sound may be transmitted through. The distance between particles is so vast, no vibration could ever make them collide with one another. In addition to the medium, the space itself and the objects within it will all have a direct impact on the wave's overall effect. As the waves encounter new surfaces, they can behave in different ways. If a wave encounters something like a barrier, the wave will reflect off the barrier, sending it back where it came from. A wave can also refract, change direction when it's moving from one medium to another. This will also affect the length and speed of the wave. Diffraction is when a wave stays in the same medium but is forced to bend around some sort of obstacle. Other times, waves will come into contact with a medium which absorbs the energy. When waves collide, it is called interference. Sound waves emitted near a smooth, arched surface will diminish much more slowly than they would in an open space. Next time you're in Grand Central Station in New York City, visit the Whispering Arch and you can experience this phenomenon in full effect. Stand at one end of the arch and have another person stand at the other. Talk into the wall at normal volume. See how the person on the other end could hear you with virtually perfect clarity at just about the same volume as was originally spoken. They call this a whispering gallery wave. The wave is guided by the wall's curvature. All sound waves generate a certain amount of pressure. Typically, sound travels through air at approximately 340 meters per second. The effect of the wave makes the air molecules squeeze together. The amount of this compression or density is what constitutes the amplitude of a sound wave. Amplitude is the measurable extent or intensity of the wave. The dynamic range represents the ratio of the softest sound to the loudest sound. This is measured in decibels, a logarithmic method of describing a ratio. Decibels are a relative measure. There is no set point for where 0 is. It is used differently in different contexts. As a reference point, in the dynamic range of human hearing, the difference between the softest and loudest sound we are capable of perceiving is about 120 decibels. Although related, amplitude should still be distinguished from loudness. While amplitude can be measured by a computer, loudness has more to do with human perception. Sounds differ because of their frequencies. Frequency is defined by how fast a sound wave oscillates in a given period of time as measured in hertz. The faster the oscillation, the higher the frequency. These frequencies are what give us our sense of pitch. A low-frequency sound wave, such as that produced by a big drum or a far-left key on a piano, which strikes a longer, thicker string, vibrates more slowly, resulting in a low-pitched sound. A crash cymbal, or a far-right key on the piano, which strikes a shorter, thinner string that vibrates at a higher rate, will result in a high-pitched sound. Most instruments, however, have a spectrum of frequencies. Each instrument produces sound waves that are comprised of a combination of frequencies, also referred to as harmonics, to form each instrument's own unique voice. This differentiation is noted in the timbre or quality of the sound that the instrument produces. So even if a violin, a piano, and a trumpet are playing the same note at the same pitch, they will all nevertheless sound distinct from one another in tone, color, and quality. Like the relationship between amplitude and loudness, frequency can be objectively measured, while pitch is subjectively perceived. Sound waves do not inherently have pitch. Their oscillations can be measured, but pitch is not assigned until processed by the human brain. The idea that sounds alone can actually trigger different emotional states is pretty mind-blowing. Music is a perfect example of this. Why do certain tones and melodies make us feel the way we do? How could a simple note have a direct causal effect on a particular emotion, the strike of a chord leaving our bodies studded with goosebumps from head to toe? The science behind this is extraordinarily complex and incredibly fascinating. Whether or not we choose to delve deeper into understanding this is up to us, but it's certain to say the universal beauty of music is that it can at least be felt by all of us.